I have this thermometer at home, and it's like one of those mercury thermometers. So you see how the mercury, there's a tube here, and there's mercury inside of it, and it's calibrated so that I believe the separation between the Celsius from here to here is calibrated to be a centimeter, 38 Celsius, 39 Celsius, 40 Celsius. So that means every Celsius, every single Celsius that it heats up, the mercury goes up to 2 by 1 centimeter. 1.1, 1.2, 1.3, 1.4, 1.5, 6, 7, 8, 9, right? From there, knowing the expansion coefficient of mercury, can we calculate the inner diameter of that tube, this tube right here? You see what I mean? How thick that inside of that tube is. Can we do that? If every centimeter, the mercury goes up 1 Celsius. Volume expansion right? So we have this tube like this, and we have mercury in there, right? So if this is 37 Celsius, let's say, and you're running a fever, it's going to go up to 38 Celsius, right? So that's a centimeter right there. So the volume will increase. Delta V is equal to beta V initial delta T. Let's see here. Would we have to measure the distance from here to here? We might have to, from the bottom up. So my question is, find the diameter or the radius of the tube. The radius or the diameter of the inside of the tube. That's my question. What is the radius of the inner tube? So every 1 Celsius, the mercury is going up 1 centimeter. That's the fact that you are given. That's nicer. Okay, so how do we do this here? Delta V is going to be equal to beta. V initial is going to be this, the original volume, right? Pi r squared H initial, right? H initial is this guy, right? And then delta T is going to be 1 Celsius, right? And then what's delta V? Delta V is the volume of this, of that portion. So what's the formula for that? Pi r squared times what? What would be the volume of that? Pi r squared times just 1 centimeter, right? This is 1 Celsius. That is 1 centimeter. So then this one cancels this one, right? And then you have here 1 centimeter. And beta is the beta of mercury. So let's look up the beta of mercury. I think that we saw this site yesterday, right?
Yes.
Mercury, 180 times 10 to the minus 6. Water was 210, but remember, water was highly dependent on the temperature. Mercury's is probably more stable, 180 times 10 to the minus 6. Okay, so this is 180 times 10 to the minus 6. No, you know what? It's not realistic for the mercury because look here, there is a reservoir of mercury down here. So the volume, the total volume of the mercury is whatever is here plus whatever is there. You guys see that? So it's wrong to say that the mercury is, the volume is just pi r squared h. You see? So what's the total volume of the mercury? The mercury that's here plus the mercury from here all the way to there. You see? So there's a thicker volume here. So it kind of looks like this. Something like that, with a reservoir. Okay, so delta V is still going to be pi r squared times 1 centimeter. That's that. You guys see that? Okay. Beta is going to be 180 times 10 to the minus 6. Right? That's beta. What's going to be the V initial? That's where it's wrong. So V initial is going to be whatever volume is here. We can call that V bottom. Right? Plus the volume from here all the way to there, all the way to the H initial. So V bottom plus pi r squared H initial times 1 Celsius. You see what I mean? So I'm adding this volume and I'm adding all the way to the H initial. So what would the problem have to give you in order, if we want to calculate the radius R? We could measure the H initial. It would have to tell you what the original height is, right? To put it here. And it would have to tell you this one, right? It would have to tell you that. And then this would be your unknown radius. Yeah, you should be able to solve that then. So in order for us to calculate that, so we could measure the distance between every Celsius. So we could measure the distance between here to here, right? From here to all the way to here. So that's going to be, I need my vernier. So something like 3.5 centimeters. So H initial is, so we have pi r squared, 1 centimeter, 180 times 10 to the minus 6, V bottom plus pi r squared times 3.5 centimeters times 1 Celsius. So the one we don't need anymore. Okay, how do we find V bottom? We would have to calculate the distance from here to here. So that's about 1.5 centimeters from here to here. And the thickness of this. So that's about 0.4 centimeters. So the diameter of this 0.4 centimeters. So in other words, more information would have to be given to you. Either the volume straight out of the bottom portion would have to be given, or you could be given the diameter here and the height of here. So if the diameter is 0.4 centimeters, what's the radius? 0.2 centimeters. Okay, now we're set to do it. Pi r squared, 1 centimeter, 180 times 10 to the minus 6. The bottom is going to be pi times what? 0.2 squared, right? Right? Pi times 0.2 squared times 1.5. I'm keeping here everything in centimeters so that my final answer for the radius is going to come out in centimeters. So pi r squared, 1 centimeter, 180 times 10 to the minus 6, pi 0.2 squared, 1.5, plus pi r squared, 3.5. Oh, okay, there you go. And then the pi cancels, pi cancels, pi cancels. Okay, you know. And then I kind of look at these things as this is real life. Everything we're using, you know. Okay, so now. Okay, so the inner diameter is 0.00328. Oh, that's the radius, sorry. 0.00. Remember, that's centimeters. This is centimeters. Let's just make sure I put the equation in right. X squared, 180 times 10 minus 6, 0.06 plus 3.5 x squared. 0.00, yeah. So that's centimeters. Which in millimeters would be what? 0.03, oh, that's very small. 7 millimeter. Remember, a millimeter is like this. Wow. Barely. It's like 300th of a millimeter. Let's see if that's realistic. Where was my thermometer? Well, it's very hard to actually check. Let's see here. If I take my this and then I go like that, I have this ancient vernier at home. God, it's very small, but there's probably thickness to that glass. So I'm getting 0.9 millimeters. That's the diameter. But of course, I don't know the thickness of, oh, it's very hard to measure it, yeah. This one is hard to do an actual percent error, but you can kind of see how thin this is, you see. It's actually inside of there, but most of it is glass. They did that to shield it so it won't break, you know. So the actual inner tube is so thin. So it's actually realistic that it would be 300th of a millimeter. Wow. Okay, so yeah, I buy that. So in other words, the number that we got from doing the calculation is quite a bit realistic number, but we can't really get a percent error from it.